Here's a beast of an equation. At first glance, it looks like a standard polynomial problem, but that a parameter makes things interesting. We're asked to solve for x for any real value of a. A natural first step for any polynomial equation is to expand everything and move all terms to one side. Let's see where that leads us. This gives us x to the fourth plus x cubed. Expanding gives x squared plus 3x plus 2a squared. And now we distribute the 2. And here we have it, in standard polynomial form. When the direct path is a dead end, we need to change our perspective. This is where the real magic happens. Let's look at our equation again. We group the terms by powers of a. We have a term with a squared, a term with a, and then all the rest, which we treat as the constant term. Let's multiply the whole thing by -1 to make the leading coefficient positive. It just looks nicer. By solving for a, we're not getting the final answer directly. Instead, we're uncovering a hidden relationship between a and x. Here's the quadratic formula set up to solve for a. Now we substitute our coefficients. b is 6x, a is 4, and c is the negative of that big polynomial in x. We square the 6x and multiply the 4 by 4. Next, distribute the 16. And combine the x squared terms. Factoring out 4x squared leaves us with this. This is a fantastic sign. It means our discriminant is a perfect square. We can distribute the square root across the products. The square root of 4x squared is 2x, and the square root of the quantity 2x plus 1 squared is just 2x plus 1. This clean result is the key to solving the whole problem. Now let's plug this back into our formula for a. We can also simplify 2x times 2x plus 1 to 4x squared plus 2x. This gives us two possible relationships between a and x, one for the plus sign and one for the minus sign. Let's explore the first case, using the plus sign. We take the plus option from the plus minus. Combine the x terms in the numerator. Divide everything by 4. Multiplying by 2 clears the fraction. Subtracting 2a from both sides gives us this. And just flipping it around gives us our first hidden equation, a simple quadratic in x. Now for the second case, using the minus sign. This time we subtract the entire expression. Distribute the negative sign. Combine the x terms. And divide everything by 4 again. Multiplying by 2 gets the job done. And rearranging gives our second hidden quadratic equation. All the hard work is done. We just need to solve these two quadratics for x using the formula one last time. Let's start with the first one. Plugging those values into the formula gives us this expression. And simplifying, we get our first two solutions for x. Now for the second quadratic. Again, we plug in the values. Simplify inside the square root. Factoring a 4 from the terms inside the radical gives us this. The square root of 4 is 2, which we can bring outside the radical. This is equivalent to splitting it into two separate fractions. And simplifying each fraction gives us our elegant final two solutions. So, we have found 4 potential solutions for x, whose existence depends on the value of our parameter a. Our first pair of solutions is given by 1 plus or minus the square root of 1 plus 8a, all over 2, which are real only when a is greater than or equal to -1/8. And our second pair is -1 plus or minus the square root of 1 minus 2a, which are real only when a is less than or equal to 1/2. Algebra gives us the answer, but a graph gives us understanding. Let's plot our 4 solutions for x as functions of the parameter a to see what's really going on. On this graph, the horizontal axis is the parameter a, and the vertical axis is the solution x. The two orange curves exist only when a is greater than or equal to -1/8. The two teal curves exist only when a is less than or equal to 1/2. In the overlapping region between -1/8 and 1/2, all four real solutions exist. Thanks for watching.